cell. We talked about graded potentials. Does all this sound familiar?
Yeah.
Yes. Okay. So graded potentials, and then we go all the way up to threshold. And what threshold is? You guys still remember that? From studying hard over Labor Day? All right, so don't forget, the graded potentials are usually initiated on the dendrites and the cell bodies. They're graded, right? They fade with distance. As they spread out, they get weaker and weaker because that signal leaks back across the cell membrane. Ions get pumped back out, for instance. The strength of a graded potential is proportional to the strength of the initial stimulus. The stronger the initial stimulus, the stronger the graded potential. Graded potentials can be depolarizations, they can be hyperpolarizations. We brought that up, right?
Yep.
Yeah. Okay, good. So we got that, and then these graded potentials travel from wherever they're initiated, spreading out through the cell towards the initial segment or the trigger zone or the axon hillock or whatever you want to call that thing, the beginning of the axon. And that's where judgment is made. Right? Are we going to develop an action potential or not? It's all determined right there at the beginning of that axon. And if the strength of the graded potential, when it reaches this area of the cell, is at some minimum threshold value or higher, right, or more depolarized than that, then you do get an action potential. If it's below that, you don't get an action potential. Okay? And so that level that is that we pay attention to, that's the threshold level. People have questions about that? You guys remember it all? Okay, so now let's go ahead and assume that the graded potential was strong enough to reach threshold at the beginning of the axon. We get an action potential. Now we get to actually talk about what is an action potential. So let's cover that. All right, some characteristics of action potentials. Within an individual cell, all action potentials are identical in strength. Right? So if you have a graded potential that just barely reaches threshold at the beginning of the axon, you get an action potential of some given strength. If your graded potential far exceeds, depolarizes way past threshold, goes beyond threshold, you get an action potential of the same strength. It doesn't matter what that initial graded potential strength was. As long as it's at threshold, you get this action potential of a given strength. It's kind of like driving on the highways in Los Angeles. You're either going really fast or you're not going at all. Right? Okay. As opposed to the Bay Area where you're just always crawling. Feels like that now, right? Okay. So they're all identical. And they're of constant strength. So yes, one action potential is just as strong as the next action potential in that cell. But these action potentials, they're going to travel down the entire length of the axon. The strength of that action potential stays constant from the very beginning of the axon to the very end of the axon. It doesn't fade as it spreads out. So this is different from graded potentials, which is pretty amazing when you think about an action potential that's sent from the lumbar region of your back all the way down to your foot. One cell to stimulate something down in your foot, like a muscle in your foot. That action potential that goes all the way down that one axon is just as strong at the beginning as it is at the end. And it's a good thing it is, because otherwise it might fade away to nothing and we'd never be able to stimulate our feet. Okay? So something's very different about how we generate and carry action potentials compared to graded potentials. And we'll get at that too. All right. So what do we have here? We've got 3 neurons. So let's say this middle neuron was stimulated at, I don't know, a dendrite, for instance, generated a graded potential, reaches threshold, or it's at or above threshold at the beginning of this axon. Now we get an action potential. So that action potential is running down the length of the axon to all of these axon terminals. All right, so when you do generate an action potential, it spreads all the way to all of the axon terminals at the end of that axon. And the strength of that action potential is equal at the end of all of those axon terminals. Okay? Okay, let's go ahead and try and figure out what's actually going on here. What is the actual action potential? So what we'll do is we'll first look at the conditions of the cell at resting. So we have something to relate it to. We'll look at how we get to threshold, which we kind of already have an idea about that. And then once you reach threshold, you get the rising phase of the action potential, followed by the falling phase of the action potential. And then it's finished up with a hyperpolarization phase. So we're going to walk through each of these 5 portions of an action potential. And so each time an action potential is generated, we go through all 5 of these at any one place on the axon. And keep that in mind. Right now, for our discussion of action potentials, we're looking at just one area on the axon. Okay? Then later on, we're going to look at, okay, how do we go from one area of the axon to the next area? How does that move or conduct along the length of the axon? But for right now, excuse me, we're looking at just one part of the cell membrane. Okay, everybody feel like they know where we're going with this? No one's lost yet? All right, let's see if we can change that. Good job. All right, resting phase. What's it look like? The resting phase, we kind of already know this. We're going to rely heavily on the sodium-potassium pump, sodium-potassium ATPase. And there are some leaking channels involved as well. All right, so the resting phase. We've got the cell. It's going to have a negative membrane potential. All right, so the inside of the cell has a lower charge than outside the cell. And it's going to be nice and stable. It's not going to fluctuate around. It's nice and steady at this negative membrane potential. And how did they get negative on the inside? It's due to that sodium-potassium pump along with a little bit of leaking channels. So remember what the sodium-potassium pumps do. They pump sodium and potassium. Sodium out and potassium in at that very specific ratio. Remember, 3 to 2. So 3 sodiums go out for 2 potassiums that come in. And it costs 1 ATP molecule for that one cycle. So every time the pump cycles, you have a net change of +1 charge out. You keep that up and you make the outside more and more positive. Or you could look at it as the inside becomes more and more negative. That's how you get that negative membrane potential. Right? The leaking channels are potassium channels. So the membranes are a little bit leaky to potassium, but that's okay. It doesn't break this down because remember that the pump makes a higher potassium concentration inside. So by concentration gradient, potassium would like to diffuse out of the cell. But also remember that inside the cell is negatively charged. So in terms of the electrical gradient, potassium would like to diffuse back in. So even though there are these potassium channels open, potassium finds an equilibrium. And with this, you still have this negative membrane potential. Did I go through that too fast? It's kind of a review, right?
Mm-hmm.
Yes?
But you would only reach equilibrium if you're dead, right?
If you're dead?
Yeah.
Why do you say that?
Because isn't that like it's constantly chasing itself with like the sodium potassium pump, like going, like potassium you said is always like driving that net one charge, correct?
Yes.
But the only time that like you would ever reach equilibrium, like finally.
Your final equilibrium? Well, by
Your final
the way you're
equilibrium.
using the term final, I'm suggesting that sort
Your
of forces it
final
into
one.
death, right? It's like Final Destination. Isn't that a movie or series of movies or something?
It is, yeah.
Yeah, I don't know. I think I see what you're saying, but let's just say we've got this living cell, it's not dead, and that pump's working away,
Right.
okay? And so with that pump's doing its thing, creating a negative membrane potential, and the potassium concentration gradient that it creates, with the leaky potassium channels, potassium will tend to move out and in at roughly the same rate once it reaches this equilibrium based on what the pump has done.
Got it,
You're willing to accept
I'll accept-
equilibrium with
I'll
life?
accept this person,
Okay. All right, any other questions for now? Okay. So where are we on this? All right, so this graph here, horizontal axis represents time. The vertical axis represents the membrane potential, the electrical charge across the cell membrane. And it really shows the entire action potential. So, but right now we're really just talking about step 1, before it curves up here. So at step 1, same as step 7 over there. We've got this resting membrane potential where it's nice and stable. It's a negative membrane potential, and it's really driven by that sodium potassium pump. All right, let's go to the threshold phase. So in this case, we're going to depolarize the cell to threshold. We're going to go from resting all the way up to threshold. All right, so this will involve a depolarizing gradient potential. Remember, some gradient potentials are actually hyperpolarizing. But we're going to need a depolarizing gradient potential to depolarize up to threshold. If it was a hyperpolarizing gradient potential, then we become even more negative, further from threshold, and more sure that we would not get an action potential. But we've got a depolarizing one. So now the membrane potential is going to rise up to the threshold value. Right. And once it gets to threshold, that triggers voltage-gated sodium channels to open. The order of these is a little bit weird. Voltage-gated, so they're sensitive to changes in the electrical gradient across the cell membrane. So we've got a bit of depolarization here. These voltage-gated channels trigger, open up, let sodium go through. Which way is sodium going to diffuse? It's going into the cell. Right? So sodium diffuses into the cell, causing the cell to depolarize more. And this is all involved at threshold, reaching threshold. All right, let's go back to our graph. So we're now at, we've gone up to number 2. Right, so the depolarizing gradient potential depolarized our cell up to this dotted line. It triggers these voltage-gated sodium channels to open. Sodium comes in. This is all happening at threshold. Remember, threshold is this magic value of depolarization, which is going to trigger something else to happen, lead to this rapid rising phase. All right, let's go to the rising phase now. All right, so remember we had our voltage-gated sodium channels open, which leads to more sodium coming in. So if more sodium comes in, the cell depolarizes even more, which is going to trigger more voltage-gated sodium channels to open. And this keeps building and leads to this rapid depolarization. So these voltage-gated channels, they're really tuned into this threshold voltage. Once you reach threshold voltage, that triggers all these gates to open. Sodium comes in, depolarizes it more gates open, and it leads to this rapid depolarization, that sharp rise in depolarization we saw in the graph. Christian?
Doesn't depolarization when that gets more negative?
No. So to depolarize, think about it as taking away taking away the polarization it had. So it was polarized, meaning there was this charge to it, negative membrane potential. If you depolarize it, you lessen that negative charge.
Less.
So it's less negative, which is the same as more positive. Kind of weird thing. Okay, anybody else all right? All right, let's look at our graph. So we're at the rising phase. All right, so we had sodium come in, triggers these voltage-gated sodium channels to open, which causes more channels to open, more channels. All the sodium rushes in. You've got all this flow of positive particles into the cell. It causes this rapid depolarization in this one area of the axon. Okay. All right, we're now ready for the falling phase. You can't just let it stay depolarized. You've got to bring everything back to where it was. So with the falling phase, first thing we've got to do is keep sodium from continuing to come in. So we need to close the sodium channels. Don't let sodium keep coming in, because that would just keep depolarizing the cell. So we have to stop depolarization. But now we have to repolarize the cell, which means get it negative again, or more negative. And that happens with voltage-gated potassium channels. Voltage-gated potassium channels. So we open up potassium channels. Well, remember, we just depolarized, so the cell now has a positive membrane potential. Okay? And it has a higher potassium concentration inside the cell due to that sodium-potassium pump we already talked about. So now if you go ahead and open up potassium channels, which way is potassium going to go? It's going to go out, down its concentration gradient and down its electrical gradient. So potassium diffuses out of the cell. When it does that, it takes its positive charge with it. You're removing positive charges from the cell, so what happens to the polarization of the cell? It repolarizes.
Sorry, you said it was going down the electrical gradient and what was the other gradient?
And concentration gradient. Okay. All right. So we're in the falling phase, number 5 on this picture. All right. Sodium channels are closed. No more sodium is coming into the cell. All right. We're not depolarizing the cell anymore. Potassium channels have now opened. They were also voltage gated. They're sensitive to changes in voltage. Potassium will start to diffuse out down its concentration gradient and down its electrical gradient. When potassium diffuses out, takes the positive charge with it, making the cell more and more negative or less positive as it goes out. And then we lead to the hyperpolarization phase. So remember, hyperpolarization is when the membrane potential of the cell actually goes below its resting potential. It becomes even more negative than its regular resting potential. And this is really due to just slow-acting potassium channels. They're slow to close. And so a little more potassium leaves than is necessary to repolarize the cell. So you get a little extra hyperpolarization. All right, so the potassium channels are closing. Right? They finally close during this hyperpolarization phase. And then what brings it back up to resting is the sodium-potassium pump sort of catching up. Because really we've got two things going on here. We've got changes in chemical gradients, and we have changes in electrical gradients. As far as the action potential, the signal that the neuron's creating, all it really cares about is the membrane potential. We're going to see that that's what the electric signal is this change in membrane potential. But what does it really due to? It's due to the distribution of these chemicals. Right? So we made our electric signal, which was a depolarization followed by a repolarization. We made that signal by letting sodium come in and then potassium go out. But in making that electric signal, we screwed up the chemical gradients. So we have to reset that. So we need to kick that sodium back out and we need to pull that potassium back in. That happens with the sodium-potassium pump. Everybody see how there's sort of two parts to that? Yeah.
Is there like a limit, like before like the cell actually start opening the potassium channel? Like how far would it depolarize before like the cell started like opening?
Open to the potassium channels.
Potassium channel.
Right. How far are we going to let this depolarization phase go?
Yeah.
That's all controlled by the actual sodium channels, and we're going to see that in a moment. So in a way, what the question is why does it stop there? Why doesn't it keep going? And we're going to see that sort of, that's a part of the sodium, the voltage-gated sodium channels, sort of built into that.
I'm a little bit confused by this picture. Number 1 is resting phase, number 2 is threshold,
Yep.
number 3 is rising phase,
Yep.
number 4 is failing phase, or
5 is the falling phase.
5.
4 is the peak. That transition
so we
between
didn't
depolarization and...
cover 4.
We smushed it all together.
Okay.
So 4 is an instantaneous point.
Okay.
So at 4, sodium channels are closed.
Mhm.
Potassium channels are opening.
Okay.
Okay, anything else for now? All right. Am I blocking you? Tell me if I do. All right, so this is sort of the summary or review. This mechanism, the action potential mechanism. Resting is really due to the sodium-potassium pump. That's what causes that resting membrane potential. Threshold is reached by allowing sodium to diffuse in. It's due to that graded potential. The rising phase of the action potential is also due to sodium coming in, but it's coming in through different channels. At this point, it's coming in through those voltage-gated channels. Those channels that were stimulated by threshold. And the falling phase is due to potassium leaving the cell, going through voltage-gated potassium channels. And hyperpolarization is also due to potassium going out to those same channels that are just slow to close. Okay, everybody got that?
So you're saying during hyperpolarization, they leave out the same channels as during the falling phase?
Potassium does, yeah.
Right.
That's right. Anything else? All right. So this figure on top, this shows what we've been looking at, right? That's the change in the membrane. Wow, I totally went blank. Membrane potential. I couldn't think of the word potential. Wow. All right, we still have almost an hour left. Okay, so it represents the difference, a change in the membrane potential. It actually says it right there. Over time, right? So we've got the resting phase, goes to threshold, rising phase, falling phase, hyperpolarization, back to resting. Down here, what I like about this one is it shows the permeability, the membrane permeability for the two ions involved over time and synchronized with that membrane potential curve. So the blue line represents the change in membrane potential of sodium. The red line, the change in membrane permeability, to potassium. So notice that the sodium permeability shoots up and corresponds with the rising phase. That rising phase is due to sodium coming through the cell membrane. And then when you get to number 4, that's when those channels close and the cell's no longer permeable to sodium. Potassium permeability slowly rises and it's most sort of active during this falling phase. Right? So when we get all this increase in potassium permeability, that corresponds to the falling phase. Why does this cell repolarize? It's because potassium's leaving the cell. But also notice that it's got this long, drawn-out reduction of potassium permeability. It takes a while for those potassium channels to close, which helps explain why we've got this sort of drawn-out hyperpolarization. Questions about these figures? All right. So we're talking about all these ions coming in and out and changing the membrane permeability. You know, how many ions are we really talking about? It's not a lot, right? It's only a few ions in any little place along the axon that's going to give us these dramatic changes in the membrane permeability. So it's not like hundreds and hundreds of ions are flowing back and forth. It's a handful that go across to give us these changes, which helps explain why sodium-potassium pumps can catch up so fast, right? They don't really have to move that many ions to get it back to how it was. But also, when we start thinking about this, the cells really rely on very exact concentrations of ions across the membrane. If that gets out of whack by just a little bit, then the whole membrane potential is screwed up and the action potential process is screwed up. Right? So if you get those ions out of whack, the cells are not going to function properly. And this was years and years ago. A student sent me a link to this video I'm about to show you. And it shows you fresh tissue that's from an animal that's recently been euthanized. And by modifying its ion concentrations on the outsides of the cells, you can get those cells to fire. And so what this is I believe it's a squid or an octopus that's been recently decapitated. And then we pour soy sauce on top. So this animal as a whole is dead. Its head's missing. But you pour soy sauce on it that has sodium in it. It's not sodium-free soy sauce. And it stimulates the neurons, it stimulates the muscles. And you keep it up, and your dinner can walk away from you. See that? Right out of the bowl. Away from those fish eggs. Pretty wild, huh? I showed this once, and then one person's like, "Did you hear about the chicken that survived for like years with its head cut off? Have you guys heard about that?" Vaguely, yeah. We don't have to go down that road. Okay. We don't need to talk about that. All right. So let's think a little bit more about those voltage-gated sodium channels. Some of it at first doesn't really make a whole lot of sense. I mean, you might argue that nothing in this class makes sense. But, we think about these channels and what stimulated the channels to open in the first place. The ones that are involved in the rising phase. The gradient potential, right? So it's depolarization. Yeah, so depolarization causes those channels to open. And what happened in response to opening those channels? The cell, it opened more channels. It depolarized even more until eventually the channels shut during all this depolarization. So somehow the stimulus of depolarization causes the channels to open, and depolarization causes the channels to close. Everybody see how that's kind of weird? The same stimulus causes the same channel to open and close. How does it know which one to do? Right? And so for a long time it was very confusing until scientists were able to figure this out. And it turns out that these channels are more complex than we originally thought. They have two gates to them. They have two gates. So not only is it a voltage-gated sodium channel, it's a double-gated voltage-gated sodium channel. All right, so what are these two gates? We've got an activation gate, and creatively named the inactivation gate. So there are these two gates, and they're going to respond to the same stimulus, but they're going to respond in opposite ways. All right, so when one's opening, the other one can be closing, and vice versa. And they do it at different rates. So what I want to do is sort of walk through each step of the action potential and keep track of what position these gates are in. And that will help explain how depolarization can cause the channel as a whole to be open and then cause the channel as a whole to be closed. All right, so the sodium channels. So these, again, these are the channels that are responsible for the action potential itself, not the gradient potential. So these are the voltage-gated sodium channels. So at resting, the activation gate is closed. Okay, so at that negative membrane potential, the activation gate is just closed, does not let sodium go through. And I should point out, if sodium's going to sneak through on this channel, both gates have to be open. If either gate is closed, no sodium passes. Right? So picture a this long tube, and there are two doors to it. The only way to get all the way through is if both doors are open. All right, so the activation gate is closed during resting. The inactivation gate is open. Even though one of the gates is open, sodium cannot get through because the other gate is closed. All right, everybody got that? All right, let's look at a little drawing. So we've got our cell membrane. The blue on the top represents the extracellular fluid outside the cell. The brown on the bottom, intracellular fluid inside the cell. The red blob represents the sodium channel, the double voltage gated sodium channel. And we've got sodium ions outside that would love to diffuse in if given the opportunity. The inactivation gate is open, right? This little ball is not plugged in there, so it's open. It would let sodium go through, but the activation gate in the middle there is closed. No sodium gets through. All right, at the rising phase, right, so we've already reached threshold. Right? What happens at threshold? Well, that's what triggers the activation gates to open. That's what's so great or magical about threshold. That's the voltage that causes activation gates to open. And that same voltage causes inactivation gates to start closing. But it's a delayed closing. It's really slow compared to the activation gates. So you depolarize to threshold, activation gates open up, the inactivation gates slowly start to close. But before they close, sodium's able to sneak through. Sodium diffuses into the cell. You guys ready for the picture? All right, let's see the picture. Okay, so this is the rising phase. So we've depolarized to threshold. That triggers the activation gates to open. The inactivation gate is still open, but is slowly closing. While it's closing, but not closed yet, sodium is able to diffuse into the cell, causing more depolarization. That's the rising phase. All right, what's the sodium channel look like at the peak? So that's that transition between the rising phase and the falling phase. We're right at the top right now. The activation gate, it's still open. Remember what triggered it to open in the first place? Depolarization. The cell is still depolarized. So the activation gate is open. But the inactivation gate has finally finished closing. That's what keeps any more sodium from coming in. When that little ball finally gets stuffed in the bottom there, the inactivation gate is now closed. And as long as one channel or one gate is closed, no sodium goes through the channel. Okay. All right. So what does that look like? So again, we're at the peak between the rising and falling phase of the action potential. Activation gate's still open. It would let sodium go through, but the inactivation gate has finally closed. No more sodium sneaks through the channel. We're done depolarizing the cell. No more sodium comes into the cell for this action potential. Okay. That's a confusing slide. Do I have a picture for that? All right. What happens at falling? So think also what's going on at falling. Why is the membrane potential repolarizing? Because potassium channels are open, which are totally separate from